We've looked at many different ways to solve differential equations thus far. So we've taken a look at just regular old analytic methods to solve first orders, regular analytic methods to solve second orders, applications of both first and second order differentials. We've taken a look at series, and we've looked at special types of series equations as well. So we're going to move on from those, and we're going to take a look at one of the final ways that we're going to solve differentials in this course. And it's going to be something called a Laplace transform. Before we can talk about Laplace transforms, we have to talk about the idea of an integral transform in general. And what an integral transform is it's basically going to be a way to take a function that's in an original space or an original variable. We're going to transform it into another function space using an integral. And then sometimes what happens is it makes it a lot easier to operate on the transformed integral, or the transformed function, excuse me. And then what we can do is we can perform operations and then transform it back by using an inverse transform. A lot of times, both transforms are utilized to solve ordinary as well as partial differential equations. In fact, it's a fairly large field of study in mathematics for applied mathematicians. Now that we know what an integral transform is, we can take a look at a specific type, and it's the only one we're going to look at in this course, which is called a Laplace transform. The Laplace transform essentially takes a function that's in terms of t and translates it into s and t. And what that can do for us by using our formula, so whenever we see this L, that means Laplace transform of a function f at t, we're going to go ahead and integrate it with respect to t from e to the minus st times f at t dt from 0 to infinity. And you may remember from calculus 2, that's an improper integral, so we have to take the limit as c goes to infinity of that. All right, so we're going to have to apply some of the things that we've learned in calculus before. Now, we sort of have this process to where we go through, we start with an original differential equation. Okay, so here's just our original differential. We're going to hit it with a Laplace transform, and it's going to get transformed into s and t. We're going to perform some algebraic operations on it. We're going to get a Laplace solution, and then we're going to transform it back into the original state. And that's going to give us our solution. All right? Before we can do that, we have to go through and we have to learn how to be able to work with Laplace transforms. So we're going to start by using the definition. Then after we use the definition, we're going to go ahead and we're going to start going through and using a table of Laplace transforms, and we're going to be able to find Laplace transforms as well as inverse Laplace transforms. And this is our formula that we're going to use at first, the definition of a Laplace transform. So let's start off with a fairly easy example. And none of these are really easy because you have to integrate, but we want to find the Laplace transform, or a formula for the transform, using only our definition. So we want to find the Laplace transform of t squared. All right. So Laplace of t squared is going to be equal to the integral from 0 to infinity of e to the minus st times t squared dt. And to be able to evaluate this integral, we're going to have to use a limit for the infinity, and we also have to use integration by parts to be able to evaluate this. All right, so I'm going to rewrite the integral. So that's going to be the limit as c approaches infinity of the integral from 0 to c of e to the minus st t squared dt. And we've done integration by parts of this a lot this semester. So we're going to define dv to be e to the minus st dt, and we're going to define u to be t squared. Now when we take the antiderivative of e to the minus st is going to be e to the minus st, and then we're going to divide by a negative s. Okay. And again, that's because we're taking the antiderivative with respect to t. All right, so there's going to be a u substitution that goes on with this. All right. The derivative of u is going to be 2t dt. And now we're just going to go ahead and integrate. I'm going to leave the limit off until the very end of the problem. All right, so that way we can just focus on the integration. Right? So this is going to be equal to uv, which is going to be 2t e to the minus st divided by minus s divided by, or minus, excuse me, the integral of v du, which is going to be, oh, I'm sorry, this should be t squared, not 2t, so sorry about that. So uv minus integral of v du, because this is a du, I see. So that's going to be 2t e to the minus st divided by minus s dt. Now, let's not worry about the limit yet. Let's not worry about a plus c or anything like that. All right? To be able to evaluate this integral, we're going to have to do parts again. So we're going to use a very similar definition. Also notice that this becomes a positive because we have two negatives, so that makes things a little bit easier for us. So we're going to end up with our dv once again being e to the minus st, and our u, excuse me, we can just define it as 2t. Once again, the antiderivative, and this should have a dt in it. Our antiderivative is going to be e to the minus st over negative s, and then our du is going to be 2 dt. So we're going to drop down the t squared e to the minus st divided by minus s. That just drops down. So we have uv, which is going to be 2t e to the minus st over negative s, minus one more integral, and that's going to be v du. All right, and there wasn't this other s that was in the denominator, so this is actually going to be minus s squared, just because remember we didn't factor in that other s. So let's just pull out that 1 over s there. So minus v du, so that is going to be 2 e to the minus st divided by negative s and dt. So finally, it works out that we can evaluate all of the integrals. All right, so get a little space here. All right, and now we can say that our final statement before we apply any of the items, I'm going to bring the limit back in. So limit as c approaches infinity of t squared e to the minus st over negative s plus 2t e to the minus st over negative s squared, and then this is going to be a plus, so we're going to end up with plus 2 over s squared, so that's just this 2, this s, and this s, and then we're going to have an e to the minus st divided by negative s, and all of this is going to go from 0 to c. And remember, this is a definite integral, so we have to go all the way back up here. Remember that the bounds for the integral are from 0 to c. So now we have to use our fundamental theorem of calculus. We're going to substitute c in, we're going to substitute 0 in, and then we're going to apply the limit. So this is going to become now lim as c approaches infinity. So we're substituting in for t. So this is going to become c squared e to the minus csc over negative s plus 2c e to the minus sc divided by c squared plus, I'll just say 2 over s cubed, minus And there should be a minus in the previous as well, sign error. So this is a minus, this is a minus. And minus, minus. And we're going to have this e to the minus sc one more time. Now we're going to substitute 0 in, and the good news is when we substitute 0, some good things are going to happen. All right, so this first term, notice it's going to be 0 squared times a bunch of stuff plus 2 times 0 times a bunch of stuff, and that doesn't matter again. Technically should be minus, and this should be minus as well. And then this last term doesn't have any coefficients of t, so we're going to have minus 2e to the minus s times 0 over s cubed. All right, so what happens with all of this stuff? All right, so one of the things you might remember is that this e goes to the denominator. Right? And remember that we could use L'Hopital's rule if we really wanted to. Okay, by the way, this is an S. If we wanted to use L'Hopital's rule and just take the derivatives as c goes to infinity, what we would see is that anything with an e to the minus sc in it is going to go to 0. So this, and this are all going to go to 0. If you don't trust me, use L'Hopital's rule a couple times. You'd probably have to use it twice on this first term, once on that term. You don't have to use it at all on this one because it's all constants. We know that this goes to 0. We know that this goes to 0. So what are we left with? Well, we're left with the opposite of negative 2 times 1 over s cubed. All right, so remember, this does not go to 0. All right, this is s times 0, and this just works out to be 2 over s cubed. All right, and so what did we do? Well, we took a function that was originally in terms of t, and we hit it with this integral transform, and now it's in term of s. All right, so this is what we say, or what we can say is going to be equal to L of t squared. So we can say that L of t squared is going to be equal to 2 over s cubed. Now later we're going to find that we have a table of these, and it's going to make it a lot easier. Okay, but hopefully this gives you a good introduction as to how to use the Laplace transform. We're going to do a couple more of these just to illustrate how to try to apply the definition.